Hey there, everybody. This is Paige. I am going to do a review of stuff that you learned last Thursday in my absence with Dr. Schwab. Okay, I know that lectures 6 and 7, atomic theory and modern atomic theory, they are very chocked full of information. And of course, my slides are best suited to myself since I made them for myself, so I just wanted to do some review. I'm going to highlight the main points that you need to know because I know there's a lot. So don't worry. I'm going to give you all the information you need. That you will need, especially on the exam, okay? So the vocab to know is where we're gonna start, first of all. So all of this vocab is going to appear in multiple choice questions at the beginning of exam 2. It's gonna be similar to exam 1, where you have to match the definition with the word. So I would definitely know these definitions. Some of them we are not getting to in this video. That is okay, because we will get to them in class on Tuesday, all right? So don't worry, but definitely know these. These are the important ones. So we're going to start with atomic theory. There's a lot of information there about like history and stuff like that. I find it very interesting, though it is not all relevant to what you would need to know on an exam. So I will summarize, okay? The first thing you'll need to know is the idea of an atom, right? We talked about matter in Unit 1, that we're all made up of matter. So I want to let you know that what makes up matter is atoms. They are the basic building block of all matter, and they are a source of energy, okay? So an atom is matter, it's energy, and it's great. They're very cool. Atoms are amazing. And so the idea of atomic theory is understanding the structure and behavior of atoms. What holds human beings together? We're all made up of little atoms, right? Well, how? How and why? That's kind of the idea of atomic theory. And it did start with Democritus. So 450 BC, a really long time ago. He's the one that kind of initially made these assumptions about atoms and whatnot, but you don't have to know those in detail. Just thought it was an interesting fact that it's really old, okay? So something you do need to know, though, is Dalton's atomic theory, 1803. All right, Dalton, he was an English school teacher. He had nothing to do with chemistry or physics, but he thought he was pretty smart. So he started theorizing things about our elements on the periodic table, right? So elements had these 4 stipulations, and you will need to know these for the exam. There will be a multiple choice question where it asks you which of these is part of Dalton's atomic theory, and you will have to know which are in the one that doesn't fit. So the first stipulation is all atoms are made up of, all elements are made up of tiny particles called atoms. That is the first one, okay? Additionally, atoms of one element are identical, while atoms of different elements are different. So if you have 2 hydrogen atoms next to each other, they're going to be exactly the same structure. But if you put hydrogen and nitrogen next to each other, they don't look the same. They do not have the same structure at all. That's all we mean, right? Third, there's a conservation of atoms. So you've probably heard this in sci-fi movies, but energy can be neither created nor destroyed. This is also, God, this is even biblical in that matter, and it continues carrying over, right? So conservation of atoms. They are not created nor destroyed, they just are. They just exist, okay? So that's what Dalton theorized, right? And then the fourth one is different atoms form compounds in constant ratios. So if you think a little bit further on this, think about water. Water is H2O. H2O. There are 2 hydrogen atoms to every 1 oxygen atom. H2O. And that will be the same every single time. You will never have a water atom, like a water compound element, that doesn't have that constant ratio. 2 hydrogens to 1 oxygen. So that is the 4th stipulation, okay? Definitely recognize and know these for the exam. So that is Dalton's atomic theory. Moving on, another one that you're going to need to know a lot about is J.J. Thomson. He did this thing called a cathode ray experiment. We're going to see it on the next slide visualized as well. And he made the discovery that within atoms, there are little negatively charged particles called electrons, okay? So this is a type of subatomic particle. We will learn 3 types of subatomic particles. This is one. So know that J.J. Thomson and his cathode ray experiment discovered negative electrons, okay? That is the takeaway from this, okay? And now let's visualize it on the next slide as well, because you will have to know kind of what happened in the experiment. So looking at the top here, hopefully you can see my cursor. I am unsure, but looking at this top schematic, what we're doing is we're taking this lovely little cathode ray, right? And we are passing electricity through it. And it shoots out and it produces a little light when it hits this phosphorus coating, right? And it's just going straight, it's just chilling. So this is just energy being shot straight through a cathode tube, producing light, period. That's it. So what Thomson said was, well, hey, what if I added magnets to this? Magnets, right? We've dealt with magnets before. If you put a positive and a negative end of a magnet together, they stick because opposite charges attract. However, if you try to stick the negative and negative end together, they repel. They will not go together because like charges repel each other. So what he did was he switched up the experiment. He said, hey, we're going to do the same thing. We're going to take electricity, shoot it through this cathode ray, but on the outside here, hopefully you can see my cursor in the bottom right, I have a positively charged plate on top and a negatively charged plate on the bottom. He was trying to see whether or not the electricity that was coming out of the cathode ray would just go straight, or if these charged plates would somehow affect it. And so what we see is that the photons here that are shooting out the electricity, it's veering away from the negatively charged metal plate. So what this says to Thomson is, hey, well, apparently there are negative charges in this electricity that are being repelled by the negative plate. And so that is where he theorized that, hey, there are negatively charged subatomic particles called electrons in our elements. And he was correct, right? So definitely understand the general schematic of how this happened. Electricity goes through a cathode ray tube, and there are charged metal plates on the outside, and the negative one deflects, okay? So understand that schematic. Besides Thomson, skip ahead maybe 20 years, we get Rutherford and his gold foil experiment, okay? So this is an alpha particle experiment. There was kind of this talk going around in the science community that, sure, we have electrons, but most of our atom is just empty space, okay? So we kind of have this even distribution of negative charges and then a ton of empty space in the atom. And he was like, well, like, is that true? I'm not really sure. So he did a little experiment with gold foil and some alpha particles from, God, what is it? He used, it was, God, I'm sorry, I'm blanking. We're still recovering from the illness, guys. Radioactive. He used radioactive elements to shoot little alpha particles out of at a gold foil, and he wanted to see what they would do. So let's look at what this looks like. Okay, our radioactive element is sitting in this little gray box. This red symbol here is the symbol for alpha. So alpha particles, all right, are shooting at a gold foil. Au is gold. And so we know that these alpha particles already are positively charged. So we already knew that. Awesome. The thing is, we didn't know what would happen when it passed through the gold foil. We thought it would go straight. It would just go straight through and it would all end up at the very back where most of these little stars are, right? But a funny thing happened. The alpha particles were deflected in different directions. Some of them went left, some of them went right, and some of them actually got turned right back around and shot back at the radioactive element. Kind of crazy, right? It's kind of crazy. And so that was not what they were expecting. But basically, since we knew that the alpha particles had some positive charge, we kind of then had to make the assumption that, oh, gold must also have some positive charge that is repelling these alpha particles, right? A centralized positive charge, okay? So this is this gold foil, Rutherford's gold foil experiment. You definitely need to know kind of the general description of what he did, all right? And from this is where the nucleus theory comes in. So after doing this experiment, Rutherford said, hey, since my alpha particles were deflecting, there must be a positive charge in the gold atom. And he was right, okay? This positive charge, this concentrated positive charge, is known as a proton. All right, proton, and it's located in the nucleus of an atom. So it always sits in the same place, okay? Always sits in the same place in the very middle of the atom, and it's positive. Unlike the electrons, which Thomson discovered, right, that were negative. So now we have two different experiments that we need to know, okay? And two different discoveries of subatomic particles, right? So definitely know that Rutherford discovered the proton, which is a positive subatomic particle, and he did it through the gold foil experiment. Our last subatomic particle that we will talk about, we're skipping ahead another 20 years. This is when the kind of the structure of the atom and the way we think about it today was really put into action, right? So we have James Chadwick. And he basically theorized that there were these things called neutrons, which had no charge. They are completely neutral. And that these neutrons make up part of the nucleus of the atom, okay? Note, remember, we also have protons in the nucleus. Protons are positively charged. And so if you look to the left at this schematic, you'll see these little black circles with the positive charge in here, that's a proton. Proton. And they are attached to our little white circles, the neutrons. The neutrons, completely neutral. So what you see here, this little clump, is a nucleus. And then if we go farther out, we can see these little like turquoise circles with the negatives in them. These are our electrons. And the electrons are orbiting the nucleus, okay? And they have different energy sublevels, and we will get to that later, hopefully Tuesday, Thursday, something like that, all right? So this is what our atom currently looks like. We have three subatomic particles that you definitely need to know. Protons are positive, electrons are negative, neutrons are neutral. Amazing. That covers the history of how we discovered things. So now we have to move on to the structure of the atom, okay? Like I just said, an atom is made up of a positive nucleus with protons and neutrons, and it's surrounded by negative electrons. So we have a general idea of what it looks like. Now the question is, how do we kind of relate this back to our chemistry class, as well as the periodic table, because we do have to have some example problems, okay? So one thing that was come up with was this nuclide notation. It is just an expression of what we can gather from the periodic table, okay? So look at this big X. This big X is our atomic symbol for elements. Per se, if we were talking about hydrogen, the X would be an H instead for hydrogen. If you're talking about nitrogen, it would be an N. Or phosphorus P, oxygen O. So the X just represents whatever symbol you see on the periodic table for your element. If you look off to the left, on the bottom, Z, this is known as the atomic number or the number of protons, all right? So this is your positive charge. Each element has a different atomic number, and they are ordered, ascending order, going from left to right, down, left to right. We will learn more about this. I'm going to do example problems from the Unit 2 handout, but it's not going to be in this video, okay? So we will learn how to do our nuclide notation, but we can find our atomic number on the periodic table, all right? The next thing is A. So this little A in the upper left-hand corner of my, my X, that's known as the mass number. So that is the protons plus the neutrons. That is not something that you can find on the periodic table. However, for purposes in our class, you will be given some information, right? You'll be given either the number of neutrons or the number of protons, and you'll be asked to find the mass number. Or vice versa, you're given the mass number and the number of protons, and you're asked to find neutrons. This is simply addition and subtraction. Again, I will go over this in a different video, okay? So this is nuclide notation. Amazing. We have a little example of it here as well at the bottom. So in this case, we are talking about phosphorus. Phosphorus's elemental symbol is P. Cool. So I put my P here. My P is where my X should be. Next is, I'm going to say, well, what's my Z? What is my number of protons? You can find this on the periodic table. You'll notice that, again, they are all in numbered order, ascending order. Phosphorus is element number 15 with 15 protons, okay? So 15 would go on the bottom. Next, and this is something that would be given to you in this case, they give us our lovely little mass number up here. So 32. That's our protons plus our neutrons. So if you wanted to know, hey, how many neutrons are in this, you would say 32 minus 15 is 17. And yes, I hope that math is right. Y'all know I'm not the greatest at math. I try my best. But that's how we would find out how many neutrons there are compared to protons. So this is what nuclide notation looks like. And again, we have a lot of example problems with those, and I will do another video on them. Okay, so there's the practice problems. The next part I wanted to get to is light waves. Okay, this is more of a physics concept, but we need to relate the atoms that we have been talking about to waves. All right, so I want you to think of this. You know what, we'll go through it, we'll see. So we have characteristics of light. When I talk about light, I mean photons, I mean energy, I mean atoms. Think of light and atoms as the same thing. Okay? So light is accepted to be a wave with characteristics of wavelength and frequency. So when we talk about light and atoms, you can also think of it as a water wave, like in a pool or a lake or an ocean, okay? So these are other definitions you'll have to know. So our wavelength is the distance between our wave crests, all right? And you will see pictures of these in the following slides. And our frequency is the number of waves that pass a fixed point in 1 second, or 10 seconds, or 1 minute, or 10 minutes, right? That number, 1 second, that could vary. You can make that whatever you want. But either way, the frequency is just the number of waves that pass during a fixed point in time. And these two things are related through speed, okay? Speed, wavelength, frequency. I know that there are other slides in the lecture 6 and 7 PowerPoint that have to do with calculating speed and frequency and wavelength. I'm going to skip that because I was not there to teach it. So you will not be responsible for knowing any of that math. I am also going to skip it on the Unit 2 handout. So don't worry about it. You will not have to know that, all right? This is what wavelength looks like. So I have, hopefully you guys can see my cursor. I don't actually know. I'm gonna do my pen, see if this pen works. So I have the crest of a wave right up here and another crest of a wave here. And the distance between the two is my wavelength. You see, wavelength, amazing. On the other hand, this is frequency. So we have two different types here, right? Frequency, again, is how many waves pass through in a fixed period of time. So look at the blue line. This frequency is lower, okay? You're not getting as many waves in a distance of time. Consider that right here is 1 second, and we're gonna go up to 10 seconds. So this is 10 seconds, and this is 1 second. You're only getting, what, 2 waves? Not even 2, about 2 waves in 10 seconds at a lower frequency. However, if you look at the green line here, woo, 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 it's going really fast, up and down, up and down, okay? And you're getting way more waves in that 10-second period. That is what I mean by frequency, okay? Number of waves in a period of time. Now, the one fact about wavelength and frequency together is that they are inversely related. Inverse means that one thing goes up while the other goes down. Or the first thing goes down while the second thing goes up, okay? If you don't know what inversely means, please look it up. So if we have a high frequency, right? High frequency, which is like woo, 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 super fast, then we're going to have a really short wavelength. Think about that, right? The distance from the two crests is much shorter. However, if we have a low frequency, woo, woo, not very many waves in a period of time, then our wavelength, look, right? Our wavelength increases. The distance between them increases. That's what I mean. And this can be done the other way too. If the opposite way as well. That's what I meant. Inversely related. So hopefully we kind of understand that concept. High frequency, short wavelength, low frequency, long wavelength. Okay? The next thing we have brings us to this concept of particle wave duality. Okay? And this is going to be something that pops up on the multiple choice exam as well, and it is going to be a fill-in-the-blank question. Particle wave duality. Please remember that. Please ingrain it in your brain. So basically, I want you to, we're going to do a quick therapy session. Close your eyes and envision the ocean. Envision waves coming at a steady pace towards you in the ocean, and you're just sitting on the beach enjoying it, right? The waves are coming, and they're all normal, and they're all the same, repetitive, one after another after another. Now imagine that you put a big rock out in the ocean, right? The rock that obviously comes above water level. It's big, okay? The wave now that is hitting the back of the rock, right? It can't go through it. So it is deflecting the water and the waves to the left and right of the rock. Okay, so it is now creating these different patterns in the water, okay? The rock is interfering with the water waves. The same can be said for light waves, right? Because I told you, think of them as the same thing. So this brings us to Thomas Young's double slit experiment in 1801. He basically demonstrated that matter and energy, such as light, he just did this with, a little, well, not a flashlight. They didn't have those back then, but think of it as a flashlight. He said that the light coming from the flashlight can exhibit both wave and particle characteristics, okay? And so what he did was we had, I'm going to flip to the next slide so it shows it better. Basically, looking here, he had this nice little wall, okay? Just a solid wall. And you see this is the light by the arrows from whatever light source he was using. And then he made 2 little slits in the walls. And he was like, well, what are these going to do? What is this going to do? Because in his mind, the light would pass right through and you would just get one solid, like, oh, cool, a big solid piece of like light. Awesome, that's shining on this back wall here. But that is not what happened. Instead, this interference pattern was created where we have light, dark, dark, and it just keeps going. And so this is the same thing that was happening if we put a rock in the water, right? The waves are going to go different directions, and the ripples in the water are going to eventually re-collide with each other on the other side of the rock, but they will be interfering with each other, right? So this is an interference pattern, and this just solidifies the idea of, right, the wave-particle duality. Oh, that's so annoying. I wanted to go back a slide. I can't go back a slide. But remember this because this is important, okay? Wave-particle duality means that light waves, atoms, matter, everything we're talking about behaves like a water wave. So remember wavelength, remember frequency, and remember wave-particle duality, okay? We are just drawing similarities together. That is all I have for you on these slides. There will be a separate video doing example problems later.